Correlation is a word that most of us are familiar with. When we say that two things are correlated, we are saying that those two things are related. For example, if a salesperson makes more calls, then they get more sales. Therefore, we say that the number of calls is correlated with the amount of sales. For a general definition of correlation, correlation is a mutual relationship or connection between two or more things, whereas the statistical definition of correlation is the interdependence of variable quantities. One way we can look at a correlation graphically is with what's called a scatter plot. Here we have a scatter plot of sales versus calls. So we have calls on the horizontal x-axis, and we have sales on the vertical y-axis. As you can see, as calls increases, so does the number of sales, as depicted by the scatter plot. Now, the correlation coefficient is an attempt to quantify the correlation between two variables. In particular, the correlation coefficient, denoted as R, is a numerical measurement that assesses the strength of a linear relationship between two variables, x and y. Some properties of the correlation coefficient are as follows. The first property is that it is a unitless measurement between -1 and 1 inclusive. The maximum value the correlation coefficient can take on is therefore 1. And if R equals 1, there is a perfect positive linear correlation between x and y. But if R equals -1, there is a perfect negative linear correlation. And if R equals 0, there is said to be no linear correlation. Positive values of R imply that as x increases, y also tends to increase. Negative values of R imply that as x increases, y tends to decrease. Okay. Property 4, the value of R is the same for data pairs xy and the corresponding pairs yx. So in other words, if we flip the axes, the value of the correlation coefficient, that is the R value, will not change. Now, the value of R also doesn't change when either variable is converted to different units. Okay. Property 6 states the correlation coefficient measures the strength of linear correlation only. And lastly, it is derived from the covariance of x and y. Okay. So correlation coefficient is actually a scaled version of the covariance, and thus it is unitless. So as I mentioned, the correlation coefficient measures linear correlation. For example, in this scatter plot, we see that there actually is a relationship between y and x, and it happens to be in the form of a donut. But if we were to calculate the correlation coefficient, the R value, we would get a value of 0, since the linear correlation is not evident. To give you some more intuition as to what the values of R will be for different scatter plots, let's look at a perfect positive correlation as depicted in the scatter plot on the far left. That would give us an R value of 1. If we had a positive correlation, we would get some value between 1 and 0. In the middle graph, we see that there is no linear correlation, resulting in an R value of 0. And with a downward sloping trend, we would get a negative correlation coefficient. And on the far right, we would have a perfect negative linear correlation, which would denote an R value of -1. Okay. So now for a pop quiz. Which of the following scatter plots and R values is correct? And which are incorrect? If you take a minute, you see that the scatter plot in the bottom middle has a correlation coefficient of 0.3. Okay. So R is 0.3, but we see that there is a downward sloping trend. So that is not what the R value indicates. So that one is in fact incorrect, with the rest of these graphs and R values being correct. And in this last slide, we see a Dilbert cartoon that points out the difference between correlation and causation. Take a minute to read the cartoon, and I look forward to seeing you in the next video.